Just summary of what I just said there. If you analyze these geometry and physics and engineering problem, you will see after you formulate it, oh, that's Riemann sum. And how do we solve the Riemann sum problem and switch to definite integral and use fundamental theorem calculus, even though this is not originally area problem. So I recommend you to understand this Riemann sum clearly, and then it's really going to help you when if you go to Calc 2, often instructors don't write Riemann sum. They write definite integral straight often. But if you go through the Riemann sum, it's a whole lot more understandable, in my opinion, from my experience. All right, so what are we going to do? The first problem is position and velocity. We already know the answer. It's a kind of different interpretation. Suppose you didn't know antiderivative idea. What if we analyze this position and velocity problem in a slightly different way, and then you see this Riemann sum there? And then you can switch to definite integral, and you can use fundamental theorem of calculus to solve this problem. Okay? So you will see under the same theme, two more kinds. What was the second one? Area between curves and average value. So here's my introduction. Motion problem once again. Mathematically, it's just antiderivative and the everything. It answers everything, but it's a slightly different point of view. I am looking at the space. The name of the space was a space-time. The thing is actually moving up and down here in the vertical axis, and horizontal part is a timeline, right? Then I'm going to divide this one into equally regular partition like this, time interval. I'm measuring this location every millionth second. Does that make sense? This is millionth second. So this is going to be tk minus 1, tk. Is that okay? So time interval is equally distributed. And I measure this location in here at tk minus 1 second was here, sk minus 1. And at tk, the thing is here in sk. However, even though I divided the time equally, the location of this thing is not necessarily equally distributed, right? It could move faster over the same time period. So it could be over here, sk minus 2, and sk plus 1. It could be quite close to that. So even though the time is regular, the position is not regular, right? Okay, that's the situation. Here's a physicist idea. They like to do this approximation a lot. In that time period, it was here in sk minus 1. It is there in sk. Suppose you have information about the velocity at time. How do you relate that to the position is the idea. Here, the velocity of v of tk. If you plug in tk in there, that's the position. But think about the velocity at that instance. Because it's 1 millionth second, it wasn't changing the velocity too quickly. For example, if you drop a ball under the influence of gravity, it goes down. If you think about it in a millionth second, I don't think the velocity is that different, right? So velocity of v of tk, a millionth seconds earlier, the velocity is almost the same. So this is what physicists like to do. Okay, I'm just going to say the velocity is just v of tk constant as it's in this period in here. Even though it's actually changing, always slightly faster, physicists want to say this is approximately right. It's constant. So how do I get this distance here? You multiply time interval, right? If you multiply time interval to the average velocity or constant velocity, you get delta sk, how much it moved over that small time period. Isn't that right? So next thing is that, oh, here, that's the delta sk, is how much it moved. So if you add up all these million, if it is between 0 and 1 million segment of movement, right, then it's going to be the total displacement. It started here and over there. So the total displacement is delta S1, delta S2, the tiny segment, the million of them, all the way to delta Sn, right? So you can just write it here that k equals 1 through n. Instead of delta Sn, you can write down v of t k delta tk, right? Which is, in the regular partition, is simply delta t. millionth second. Now that's analysis. That's what went through the physicist's mind. That must calculate the displacement if it is constantly changing. That's how it started. But by staring at that one, what do you see? What is a good name of this thing that just rose? What is this? Integral, Riemann sum. This is a Riemann sum, right? If you chopped into the more and more small time interval, that is supposed to approach this thing is a stretch to that, right? Between time interval to A to B, this all the tk or tk star, it changes to vt, and this delta t changes to dt. So Leibniz wanted to keep the structure of the Riemann sum embedded into this definite integral notation. That's Leibniz's invention. Came from the summation, came from the delta t. Yes, yes, it's right. Okay, so but here's the second thing. So that's that. That's how much it moved. But what is the displacement? What was the very beginning location? That was the location at the beginning time SA, right? What is the terminal location? S sub B. That's a terminal time. So we know this answer is supposed to be what? SB minus SA. So I obtained that not going through the fundamental theorem of calculus, right? This is a definition of definite integral, and theorem of integrability of continuous function says that this must approach that, and I got this answer from common sense. It started from here and ended in there. That's the difference of position. That's the displacement. But what is the relationship between vt and st? Yeah, derivative of velocity is equal to, derivative of a position is equal to velocity, right? So we proved that antiderivative of vt of b minus a is this definite integral, right? I didn't use mean value theorem. I just used a physics principle. What they thinking was correct. Often people say this one is a physics proof. The ingredient inside is the physics principle, not mathematical principle. So this is a physics proof of what? Fundamental theorem of calculus. One that I gave you before is mathematical proof. But in the test, mathematical proof, not physical proof. So that's physics proof there. Using that instantaneous analysis, sometimes what they call, we got this one obvious and in there, but that must be this one according to the simple, according to the context in the physics, this must be that. So relationship between that one and here is antiderivative. And realize that, oh, I didn't actually use fundamental theorem of calculus. I proved fundamental theorem of calculus using this.